looking for other objects in our solar system. Suddenly people realized that there was more than just the planets you could see with your eye, that telescopes could reveal more and could reveal more objects. And so a search was undertaken looking for the quote unquote missing planet in this awkward gap between Mars and Jupiter. And it wasn't long, only about 20 years after Uranus was discovered, that that first object was found, Ceres. And so we thought we had this settled until a few decades later, 4 more planets were found in this gap. And then we said, okay, well, maybe there's 5 planets in the gap, but further surveys continued to populate this. And as we looked with more and more telescopes, looking deeper and deeper in different kinds of ways, the number of objects we found grew. And we had to redefine what it was to be a planet. No longer were there 20 planets in the solar system. These were downgraded to a class of asteroids. And you can see a sudden ramping up here, right in the 60s. A survey was done that filled in a bunch. And surveys continued slowly until the 90s, when there was a new surveys put online to search for near-Earth objects. And in doing so, they discovered most of the asteroids we know of today. And so that's how our solar system, our knowledge of the solar system, has been filled in over the last 200 years or so. Now, each of these objects, in addition, once you measure them, once you discover them, really all you have is an orbit and an idea of how bright it's supposed to appear, an apparent magnitude. And once you know the orbit, you can basically judge what that apparent magnitude change over time is going to be to, a good first order approximation. But as you investigate them with other aspects, you look at them through spectrally or looking at their albedos, you start to just see differences among the asteroids. And so an optical to near-infrared taxonomy, so spectra taken of a large number of these objects, from the visible light to the near-infrared light, reveals a suite of different behaviors, of different spectra. And so each of these letters here corresponds to one of the taxonomies that was drawn out of this large survey by Francesca De Meo for her thesis. And you can see kind of the clustering here. The position of these spectra on here is not random. This is actually in principal component space, showing if you analyze how the objects relate to one another, each of these flat objects that just kind of have different slopes all kind of fall on this line in principal component space, whereas there's a break here, and you have objects that have deep 1 and 2 micron absorption features associated with iron in the silicates in the surface, so olivine and pyroxene. And so initially from this alone, you can start to see that there's different compositions that we're playing with, that we start to see things that look, again, these S-type objects look like rocks we have on Earth, obviously less processed, but they look familiar. Versus this whole group here show really no spectral signatures through the entire wavelength range studied. And so something else is going on here. And it turns out after extensive research that these in fact are dominated by silicates. The thing is that the carbon embedded in the minerals absorbs all the light. And so it makes them darker and it mutes those absorption bands. And so you wind up having different compositions between these two, different spectra between these two that trace the composition and the subcomposition of the minerals. Francesca took her spectra, and then looked at how they're distributed as a function of mass through this main belt between Mars and Jupiter. Now, if you'll notice that there's gaps in the belt here. These are the mean motion resonances with Jupiter. So the gravitational interactions as Jupiter orbits, for instance, 1 time and the asteroid orbits 3 times, you get regular gravitational tugs that quickly drive objects out of this range. And so that's what these gaps are. But otherwise, this gray curve corresponds to a mass density effectively. And in here, we're using mass because asteroids have undergone collisional processing. And so in some cases, a single asteroid has been impacted and has shattered, spraying thousands of new objects into the belt. These objects will poison statistics if you do them sheerly by counting by number, but the mass is conserved. And so if you do this kind of plot by mass, now what you're looking at is what was the composition at the time and how do these things vary. And you can see that in the inner main belt, these red objects, these S-types, the silicate things, dominate by nearly an order of magnitude over the darker objects. Whereas as you move out closer to Jupiter, that changes. And as you get to the edge of the main belt, the silicate objects almost entirely vanish, and you're entirely dominated by these carbon-rich objects that point to a history of having water in them. Our best understanding of these objects is that they are, kind of serpentines, which is a silicate that has been exposed to water as it was forming. So not necessarily that they had oceans under them, but that the material that made them was wet and warm when the minerals were forming and caused a serpentinization of the silicates, as well as a carbonification. So you're getting carbon-based elements as well, carbon-based minerals as well. And so you can see this trend across the belt. And this traces, we believe, different eras of implantation. During the very early solar system, as the protoplanets were moving around, this area wasn't as stable as it is now. And it's believed that series, if not all of these C-type objects, were implanted from a population that originally formed beyond Jupiter and was brought in during that chaotic period. And so what we might be looking at is objects here, the bright S-type objects, are stuff that's more like what formed Earth. And these C-type objects are more like what is at the core of Jupiter and Saturn before they got their gaseous envelope. You can also then compare these different taxonomic types with meteorites that we've picked up, doing the same kind of spectra, looking at these meteorites and saying, which one do these look most like? And so the bottom row here shows different kinds of meteorite classified by, if you actually take it and look at the minerals in detail with a microscope, you can sort out whether these LL, Ls, or Hs are the various C types. And then taking those and comparing the spectra of each of those various meteorites that you picked up with the closest matching spectrum of an asteroid we've observed from Earth. Now, there's a difference here. The meteorite is, if you cut it open, you're looking at a fresh surface of something that was strong enough to survive re-entry, entry into the Earth's atmosphere. Whereas the asteroids we're looking at, you're looking at a processed dusty layer that's on top and has been exposed to space weathering for a long time. And so they're not necessarily a perfect match, but they should be very close. And you can see that. You can see that these first three columns here, which represent the ordinary chondrites, match closely with these reddish objects. The blues kind of fall in here, and then you get the purple objects matching to the enstatites, the V, these Vesta-like asteroid spectra, matching with the Diogenite, Eucharite, and Howardite objects. These are meteorites that we now know came from Vesta itself, and so those match up nicely and are expected to match. And then some more weird ones about the spectra that associate, and where did the iron meteorites come from, for instance? Where did the Uralites come from? So there's a lot of questions and a lot of strange meteorite types that this is trying to address. But we can use these and all these various pieces of information we have to build a more complete picture of what asteroids are made of. And so this is where my work comes in, is looking at the polarimetry of the asteroids in space and comparing that with what we know about the mineralogy on the ground. This is results from a survey that was done by Gil Hutton and his student Kanyada Asandri about 10 years ago. And they took a series of observations of different objects with the same spectral type from the near infrared, and then compared and then basically overplotted all of the polarimetric observations that we see. And what we got are these curves. And you've seen these before. Eredian and Hol showed you these in their previous two talks just before lunch. This kind of behavior of starting at 0 and going to a negative polarization, returning to a positive value as a function of phase angle. And you can see that the shape of these curves depends on that taxonomic type, that the mineral properties on the surface are what dictate this behavior that we observe in polarization phase space. So I don't think I have to go into this audience about what polarization is. This is one of the few talks I get to skip this, but I will say that all of the polarization we're dealing with here is from scattering. So we're not looking at transmissive polarization necessarily. It's all stuff that has hit a surface and scattered off. Very similar to like what you get from scattered light while you're driving on a wet roadway, for instance, or light that's polarized by the surface of the ocean. And naively, you would expect polarization to be oriented perpendicular to the scattering plane. But for asteroids in particular, we get this strange effect. And this is kind of a strange diagram, but what's happening is you're getting light that comes in from the sun, and it hits one of two scattering elements on the surface, is scattered to the second, and then goes to the observer. And then the reverse trace of light that hits the second one gets scattered to the first and scattered to the observer. And if you compare the various possible orientations, what you see is that this alpha angle here, that's the phase angle we are interested in. That's the opening angle between the sun and the Earth, as seen from the asteroid. The alpha angle, the phase angle, doesn't change the path length of any of these lights for this orientation of the minerals, but for any sort of two scattering situation that's oriented like this, there's a difference in path length of this d sine alpha, of this distance between the scattering elements, whatever they are, which I'll talk about that a little bit later, and alpha, again, that phase angle. And so what that does, in effect, is it suppresses the single scattering polarization that you expect, and instead pushes polarization into basically being in the scattering plane instead of perpendicular to it. And so this happens for phase angles smaller than about 20 degrees. And this is what we refer to as negative polarization in the asteroid community. And again, I think I can skip this one, as I'm sure most of you know how we measure polarization. You can either have a rotating half-wave plate that goes through a single wire grid, or more preferably, a rotating wave plate that goes through a beam splitter where you measure both states at once. And obviously, the second case, you get much better precision because you now have temporal stability. You can do your comparisons and not have to worry about changes in brightness over time. So what this dual scattering effect does is causes this kind of shape that you've seen in the past couple talks, where at 0 degree phase angle, by mathematical definition, the polarization has to be 0, because you don't necessarily care what direction you're oriented in. There is no there is no scattering plane effectively. But as you grow in phase angle from 0 to about 20 degrees, polarization enters what we call the negative branch. And this is regardless of what the orientation is on the sky, north over east. We orient our analysis plane to be perpendicular to the scattering plane. And we say anything perpendicular to the plane, which is the expected single scattering polarization, we call a positive value. And anything 90 degrees from that, we call a negative value. And so the polarization enters this negative branch, bottoms out at some P min value, returns to 0 at around 20 degrees phase, so this alpha 0 value, and then proceeds to be positive after that and follows what you get from your standard textbook Brewster scattering. So the tools we use to analyze these curves are this P min value, where this inversion angle is, alpha 0, and what the slope is at that inversion angle. And using those three parameters, we can start to basically quantify what these curves are doing and compare them to one another. And as Jorge showed in his talk just before lunch, there's a correlation between both P min and polarimetric slope with albedo. And so this is from Alberto Cellino's work in 2015, showing that there's this nice linear trend where you can go 1-to-1 effectively. If you measure the P min or you measure the polarimetric slope, you can infer an albedo. Caveat these objects here that are below the curve. And we're not quite sure what's going on if these are objects where the albedo has saturated, or if you're seeing a change in mineral behavior. Shevchenko, I believe, had a fit where he tried to fit a curved parabola to this. But it's unclear if, what I will say is a lot of this now is starting to depend, for objects we have good polarimetric values on, the albedo is now the most uncertain thing. Albedo we get in most cases by measuring a diameter from something such as NEOWISE, the main project I work on, getting a thermal infrared diameter for the object, and then solving for albedo by what the optical light, the absolute magnitude of that object is. But the absolute magnitude has a fairly large uncertainty, 0.2 magnitudes, for instance, which translates to about 20% uncertainty on albedo. And for low albedo objects, that uncertainty is worse. And so these could be cases where the object is just uncertain beyond the quoted error bars on albedo. So I would take that with a grain of salt, but this linear trend has held up over time. In addition, I did some work for my thesis where we looked at basically simulating a series of scattering surfaces and how that affected the curve. And one of the most interesting things to come out of that is that the location of this alpha zero, of this inversion angle, depends on the smallest element scattering the surface to a small degree, but to a large degree, it depended on the index of refraction of the surface material. And so where this crossing point is directly traces the index of refraction of the surface. And that points very uniquely to minerals. A large index of refraction versus a small index of refraction really rules out a bunch of possible minerals, especially with the kind of simplified options you have for asteroid composition, right? We don't have a lot of igneous options. We don't need to worry about metamorphic rocks. We don't need to worry about really sedimentary. We don't have any of the processing that's gone on. So there's really only a small selection of minerals that can exist on asteroids. And so by constraining this index of refraction, that provides some very unique insights into what is happening here. And this became very important when a new class of objects was found by Alberto Cellino in 2006, starting with the object 234 Barbara. And then there's some follow-on work I did on Aquitania, and other work did on Anacostia, and more objects started rolling in, determining that there's this class of objects that had polarization that didn't behave like we expected. It didn't follow either of these two curves. So here, this dotted line is what you'd expect from a normal silicate-rich object. This dashed line is what you expect from a normal carbon-rich object. And these were clearly off that line. They were following their own curve. And they were implying that this crossing point was around 27 degrees. And as I said, because this crossing point points to index of refraction, this implied that the surface was covered in a very high index of refraction material, which has been traced to spinel, which is one of the earliest minerals to form in our solar system. It only forms in high temperatures, and so it was probably the first thing to condense out of the protosolar disk as it was cooling down, as the sun was forming. And so there's a lot of questions that get involved in why are these objects showing surfaces rich in some of the oldest minerals in our solar system? Why haven't they been buried by other stuff? Why hasn't dust fallen on them? And how did they get there? Are they relics of the very first objects? Or are they the last remnants of things that were gathered up right at the end? We don't have a good answer to that yet, but it's something we're working on. So let me get into my current work now using the Palomar telescope. This was a photo from a recent observing run taken with my phone in night mode, which I really love the technology these days where you can just they do all the phone fixing stuff and you can get really nice photos just from your cell phone. So plug for that. But this is using the work pole instrument. And so work was the wide field infrared camera. And the idea was to do J, H, and K observations over a big field of view. But a group of researchers also installed polarimetric capability using this really unique, I've never seen one of these before, polarizing grating, they call it. And so what this is, you can see this optical element here has this split down the side. And so what's going on is it's actually two optical elements put together, a quarter wave plate, where half of it has its axis in this direction and half of it has its axis at 45 degrees to that. Pasted on top of that is a grating, a low-level grism, again, that is a polarizing grism with axes at 90 degrees to each other. And what this results in is a single star entering this. And this is placed, of course, off focus, so where the beam is collimated. So when you focus it, what you get now is a single star gets split into 4 traces here. So 4 spectra that represent the Q and U states. And so you're getting simultaneous measurements of both Q and both U states across the spectrum for the objects you observe. This is incredibly fabulous and is really powerful. And then upstream of this, a half wave plate has been installed. So now you can beam swap between these 4 options. And so that really lets you beat down the systematics and drives us to be able to get better than 10% accuracy on our polarization measurements, as well as getting spectropolarimetric sensitivity, which I won't spend too much time discussing here because I really haven't worked it out yet. And so this is what I said, yeah, so we have a half wave plate here that now pushes the beams into each of the 4 configurations. And so that's what allows us to get the high accuracy that we need to do this asteroid work down at those low phase angles. So this is what the basic data look like. So my opening slide showed that little 4-star spray. That is what the data looks like on the chip. When you do the data reduction, what you get is a spectrum for Q, a spectrum for U, a spectrum for the polarization, and then a theta as a function, all as a function of wavelength here. This was for a standard star I was looking at, I believe. And the orange line is what we expect the polarization and theta to be based on literature values. And you can see the blue points are reproducing it pretty well. There's some variations here in the spectrum. I'm not sure if they're real yet or not. You can see that they're kind of 1 sigma at this level. And since the standard stars aren't really what I'm digging into, I haven't looked at this one yet. We haven't seen any conclusive change in polarization as a function of wavelength for the asteroids yet. But we're still gathering data and still in pretty early days. So I expect as more data comes in and we start getting more objects, we'll be able to start answering those questions. But what we can do then is just take each of these spectral bins and co-add them together, error weighting the addition to get a single value for each of the wavelengths. And so work pole can observe in J and H band. It turns out we can't do K band because the polarizing gradient spreads the light too far away. And so it starts falling off the edge of the chip. But J and H, it works really well for. And we can get down to a magnitude of around 14, which is relatively bright for a 5-meter telescope. The reason for this is, of course, all of your light is being spread into these spectral traces. And so you're really stretching it out over a bunch of pixels. And so it gets pretty faint pretty fast. But we'll probably be pushing further down than that as time progresses. But right now, this is the first time anyone's done any of this. So even the really bright asteroids are having some interesting results. And some early results I'm happy to show here. So what I'm showing, again, this is this polarization phase curve that we expect. My data for H are in the black triangles and J are in the pink pentagons. And then the U, B, V, and R data, any other data you see here was taken from the literature. There's an archive of all polarization measurements that have been made of these objects on the planetary data system. So extracting from that to make these plots. And in this case, I'm showing 3 C-type asteroids. And you can see that, from the ultraviolet all the way to H band, these objects seem to have very consistent behavior. There's a little bit of outlier in the UV, but the uncertainty is pretty high because asteroids are pretty faint in the UV. But other than that, we're seeing, very consistent behavior that the, black and pink points are falling right over where we expect them to. And the fits that are done, basically these are blind fits to the data, follow the exact same trends as we expect for the visible light measurements. And so this is comforting to know that, hey, we're doing it right. Our calibrations are good. But it's also somewhat expected. These are low albedo objects where we don't get a lot of change. We don't see a lot of spectral changes for these objects. Their spectra are flat. And so it's basically good to know that we're reinforcing that these are fairly boring objects that are consistent across wavelengths. For these S-type objects, so here I'm showing a combination of data from 4 different S-class objects. Again, these are the silicate-rich. We're starting to see a little bit of changes. From UV to red bands tend to follow one trend here, which crosses at around 20 degrees. And the near-infrared bands seem to have a slightly different trend that's showing a fit at a slightly higher phase. This would imply a slightly larger index of refraction for the material. This is not very surprising. We know, especially silicate materials like glass have different indexes of refraction as a function of wavelength. That's why we can get rainbows out of a prism. That's why many of our prisms work, right? Is anything transmissive like that. We know that there's a chromatic difference in the speed of light through the material, but it's nice to be able to measure it for the surface here. And this change as a function of wavelength will help us pin down exactly what it is we're looking at. exactly which minerals we're dealing with here. And that consistency I talked about with the C-type objects also has another important benefit, and that is calibration. So one of the difficulties in doing this work is there are actually very few calibration sources at near-infrared wavelengths with these high precisions. There are many polarimetric standards at visible light that have been measured for, decades, basically. And so we know that they're stable and we know that they're reproducible. But the problem is many of the polarimetric standards are stars where the light is passing through magnetized dust, dust in a magnetic field that's acting as the polarizer. Well, this transmission is a function of wavelength. And so the polarization winds up dropping with wavelength as the dust becomes less opaque and so less powerful polarimetrically. But also we've been able to see twists in some of our spectral standards where the angle of polarization is actually changing with wavelength due to what's going on the surface. And so instead of using standard stars that are not necessarily standard, we can take these C-type objects, these primitive asteroids that we know should follow this consistent behavior. And in particular, we know what the angle of polarization is very, very well. Because we know the orbit of the Earth and the asteroid, we know what the scattering plane is to less than a fraction of a degree. And so by knowing the scattering plane and knowing that it's either going to be at 0 or 90 degrees, we have a very powerful constraint for what the angle of polarization should be, letting us calibrate the angle of polarization for the instrument. And we see that here, looking at the change in theta that's predicted versus what is observed, we're able to pull out that this instrument has a 3 to 6 degree shift that's slightly twisted with respect to north, even after the calibrations are being done by the data reduction pipeline. So this is something that using asteroids as a calibrator allows us to do. We can also do this with the expected polarization for anything that's far enough from 0, especially in this 1-2% value. This is significantly more polarized than a lot of the standard stars at these wavelengths. And so these make good standards as well for expected polarization. The only issue with using asteroids for this is that they change over time. Their phase angle changes, and so their predicted polarization changes. And the angle of polarization is constantly changing as all these objects move around the sun, but also can flip from positive to negative. And so you have to basically check day by day which ones will be standard and what the standard value should be. But again, they can allow us to do this kind of calibration. So in order to help with this, I put a quick little tool together on my personal website where you can just enter in the date and it will spit out what asteroids you should be looking at, what the expected polarization is, and what the expected angle is on the sky of the polarization. And this is just meant to help, again, because these objects are kind of flat across wavelengths, you should be able to, the magnitude shouldn't matter. So the V magnitude and the J magnitude are about the same. They're basically just flat reflectors of sunlight. So this tool will basically allow you to do this kind of work. Right now, there's only a few asteroids on it because I need to confirm that these actually are behaving as we expect before I add them to this list. But this should grow over time. So if there's any interest in it, it's available. Excuse me. So this leads to the question then of what will this same plot that Ricardo Gahunton made of the various taxonomic classes as a function of phase angle look like when we look at near-infrared wavelengths? Well, how will these objects change? How will these curves change for these various different objects? And so that's kind of the question going forward. And as my survey progresses, what I hope to answer. I'm happy to share some early results with you. And you can see some things are well-behaved and some things are not. So Pallas here, this is, again, one of these C-type objects that we know is consistent. You can ignore the red and the purple dashed lines here. They're being fit to a minimal amount of data. But if you look at the green compared to the near-infrared data that we're getting, again, these match up nicely and are doing pretty much exactly what we expect. Vesta, as we saw before, with the S-type object shows a slight shift. You can see that there's a trend over to longer, to increasing inversion angle with wavelength. But some objects are being strange. Eunomia is a boring silicate-rich object, and some early data is showing that maybe it's not as boring as we thought. Again, this is just one outlier data point with a decently big error bar, but this is something that warrants further investigation. Same with Juno here. I showed this in the previous plot. While the general S-type trend was showing it to larger phase angle, what we're seeing is that maybe for this object specifically, it's not necessarily that much of a big phase angle shift, but rather a deepening here. And so what we might be seeing now is instead the slope is changing. And as was mentioned before, that slope is correlated with albedo. And so this object might be changing in albedo as a function of wavelength in addition to index of refraction. So this is something we're just tracking. But what's really been most interesting to me is the results for the barbarians. So these really weird objects with very high indices of refraction. And especially for Aquitania here, we're seeing that this index of refraction, this inversion angle, is pulling in with wavelength. That actually seems to be having a fundamentally different behavior. And we see that for some of the other ones too. Honoria, Barbara, there's not too much data on Barbara yet, but I'm hoping to get more as it becomes visible this next coming semester. But that we're seeing this change here that might point to kind of dramatic shifts, not necessarily in the surface mineralogy, but in what minerals are visible at which wavelengths. And my current interpretation of this, where my speculation right now that I'm hoping to settle by getting some more data, is that we're seeing different minerals. We're seeing, if a surface, for instance, is covered in very small dust, it will have, for instance, 1 micron scale. Sub-micron size light will be sensitive to what's going on inside the dust, the minerals that are contained in the dust, and micron size, super micron wavelengths will be seeing each dust particle as a unit instead of the minerals as a unit. And so that might be what's going on here. But whatever it is, it's really fascinating. And I'm excited I just got some more data Friday night, so I haven't reduced it yet, but hopefully we can add a few more points on this plot.
5 minutes.
So just to conclude, asteroids are the relics of the formation of the solar system. And they really offer us a critical perspective on the evolution of Earth and the other terrestrial planets. What were they built of? How did they form? And what was going on at the time that these objects were formed? Again, they offer these snapshots of the formation of the solar system. And polarization provides us a unique constraint on the surface mineralogy. This measurement of index of refraction is something we can get in no other way other than going to the surface with the spacecraft, picking up a piece and bringing it back to Earth. And so this really is kind of the only way we can really probe this part of the mineralogy. And it really gives us some powerful insights into what's going on. The changes in this polarization with wavelength now allow us to do this comparative mineralogy that is comparable to what has already been done with spectra. Obviously on a smaller scale, since polarimetry, as you all well aware, is very expensive to obtain in terms of time. And you have to, especially for the asteroids, you need multiple measurements. But, we're starting to be able to, take these from kind of snapshot stuff into looking at this spectral changes in polarization. As I mentioned, primitive asteroids show predictable behavior, and so can act as powerful standards for angle and degree of polarization across wavelengths. And near-infrared polarimetry is really revealing some unexpected behaviors, and I'm kind of excited to see what new insights we get out of this. There's a lot we don't know and a lot we're seeing for the first time here. So I'm happy to take questions. Thank you.
Thank you, Joseph, for this illustrative talk. A lot of nice resolved questions. Well, I have
a question.
Few questions. Sorry, I have few questions. In the instrument that you show, the work, I
Yeah.
did not understood what was PG.
So PG is this thing. It's a polarizing grating attached to a quarter wave plate. So it's a prism effectively.
One is above the other?
Yes, they are. You can see them right. There's like a thin line right here. They're glued together. They're two optical elements cemented together.
And by exposure, you get these 4 states of polarization, and then you rotate the quarter wave plate.
No, we don't change this orientation. Instead, we rotate the half wave plate. So there's a half wave plate upstream of it. So we rotate the half wave plate, and then that light gets sent through the PG, through this optical element here.
Yeah, thank you. Questions? Wait.
Hi, good afternoon. Just a question by pure ignorance. Those asteroids, they do not emit. I mean that, for example, what you've shown is only the scattering, but there's no emission in those objects.
Not at these wavelengths, no. They do have emission out past 4 or 5 microns. So there was thermal emission at those wavelengths. And a colleague of mine at Caltech, Catherine DeClear, is starting to look using ALMA to look at for polarization of asteroid thermal emission. Because ALMA, you can resolve the surface and you can see polarization at the limb. But no, we don't expect there to be significant polarization for emission as a point source when you integrate across the body.
Actually, I was about to ask about if you were doing polarization in those longer wavelengths for those objects. Okay, thank you.
You're welcome.
Hi, hello. So I have 2 questions. One is about the PG element. So I want to understand if it's a grating acting as with a spectrum separation and a polarizer.
Yes, it is a grism that preferentially polarizes the light passing through. So it splits the two different polarization states. So it will send, for instance, this one here sends the 0-degree light this way and the 90-degree light that way. And then this one here sends the 0-degree that it sees this way, and the other one it sees, the 90, it sees this way, but these two have been rotated by the quarter wave plate in the process.
Okay, thank you. And the second question is more basic. You mentioned that some of this measurement can be done in the visible range. And so is it possible to use a normal telescope, like a not that big telescope, like a commercial one available?
So the only problem is trying to get enough photons. So to get this 10th% polarization you need to build these curves up, you need to collect about 1 million photons. And so it depends on your limiting magnitude. For if you have a 2-meter class telescope, you can get down to 18th magnitude or so with the right instrumentation.
Oh, thank you. Thank you so much.
Yeah.
Enrique sent in the chat a link to the PhD, so we can find more information. Before to give the microphone to Joel, I would like to ask about the spectropolarimetric data that you showed. I mean, there were several measurements in the whole range, and then when you present the results, I'm not sure if this data we saw it in the results.
No, you haven't. What I do is I take all of these measurements and I smush them together into a single value for the band.
Okay.
And I do the same for the theta, and I use that to beat down the uncertainty, because you can see the uncertainty in each spectral bin is, 1/10 or 0.2% here. So to get the polarization to the sensitivity I need, I co-add all the data together. But we still have this information, and so future work will be, do we see changes across the spectra? Once we understand what they're doing across as the bandpass is considered as a whole, then we can start looking within the bandpass.
Yeah, it's very interesting, those groups.
Yeah.
They are meaning. Joel, please.
Thank you, Julio. And thank you, Joe, for this interesting talk. Thank you for accepting. Give us this talk to us.
Yeah.
And I have a few questions, but the first one is when you use this GRISM and you show us the phase polarization curves.
Yeah.
You are giving us the filters, the bands.
Mhm.
Do you actually use a filter, or you are taking it from the footprint of the image in the CCD?
Yeah, so we actually use a filter just below the PG element. There is a J or an H filter that blocks all the rest of the light. And so
Okay.
we only get, so if I go back to my opening slide, so this is, for instance, J band. And so that is the zero order that is not being scattered, because I think this is series, so it's kind of crazy bright. But this is the first order of each of those spectra. And so you can see it's being cut off by the J filter at high and low.
Got it.
Yep.
Got it. Okay, great. Yeah, because I was thinking if you can get all the light, because you should have different CCDs for getting different bands, of course, right?
Yeah.
The other thing is, would you say something about circular polarization in asteroids?
About which one?
Circular polarization in asteroids.
Yeah, so I looked at that for my thesis and didn't find anything, but I didn't look too hard. A colleague of mine, Sloan Wiktorowicz, is using the instrument called Polish 2, which is instead of rotating the wave plate and then taking an exposure, it has a constantly cycling wave plate, and he puts it on the Lick telescope, and with the photopolarimeter he can get down to like 0.1% accuracy, both with full Stokes sensitivity. And he is starting to see some early results of his are seeing, if not, non-zero V values, but changes in the V. So if you, over time, it kind of cycles around a small fractional polarization, a circular polarization, but he's actually seen changes in V across the surface with rotation for some of these objects, in particular, some of the Psyche. And so, so we would think, I mean, I'm sure, as you know, that we would expect maybe V-type polarization, circular polarization for metal-rich objects. So, that he's just kicking off a survey to look at a bunch of the M-class asteroids, the things we think are metal-rich.
I read a couple of papers about that, and they were claiming that different organic materials were playing a role on that. Yeah. And I'm not sure, because there are no more papers on that than I expected to read more, but I could find just 2.
Yeah.
Well, the other thing is, first I forgot to ask you the limit magnitude of your instrument. What is it?
Right now, I'm kind of stuck at V of 14, so it has to be brighter than V of 14. And again, that's mostly because once you get to that level, you lose that zero order. And these become very faint, and then it becomes incredibly difficult to know if you're tracking on the right source, because, these objects are moving, and, this is a very simple image, but in cases where you have a series of background stars, it becomes really difficult to tease out what's going on in some cases. So we probably, for certain cases, could get deeper than that if we, tried hard, but for the asteroids where sometimes they're moving through star fields, I tend not to observe below V of 14 right now. I know I can get good results at brighter than 14.
Okay, great, thank you. One last question. Will you say something about the role of geography and porosity in the polarization curves?
Yeah, that's interesting. So until recently, for geography, there have been very few cases where we found, as you know, found solid evidence of rotation, of polarization changes of rotation. Vesta is always held up as well. We saw it because Vesta has this huge crater that has a pretty significant mineral change in the crater floor versus the main body. But other than that, there's been a little bit of work. You've done some, Sloan Wiktorowicz is starting to do some right now. And I think now that the instrumentation is getting better, we're starting to see more of these results come. And I'm excited to see, I think that probing, especially the, objects where we think that there might be changes across the surface, right? Because we know that most objects kind of are relatively homogeneous. But space weathering, for instance, could be a big change, right? Could result in some of these mineral changes that are visible. And so if you can find something that has been recently impacted, where you have a fresh crater with an old surface around it, that could be an interesting case. So asteroid Sheila was hit about 12 years ago by a body, and they think that dug out a couple kilometer crater. And so that could be an interesting object to look at for a fresh versus old surface. Ryugu, right, since they just blew a hole in it, Hayabusa 2 blew a hole in it. Or I don't know if we'd be able to sense changes due to dimorphos with the DART impact, but cases like this or active asteroids where you think are caused by impact, I think those would be really interesting to see old versus new surfaces and how that teases out in polarization.
Yeah, I wanted to conduct a campaign on polarimetry on Didymos, but I didn't have the time. But do you know if somebody did it?
I don't know. So if it was anyone, it was probably Max de Vogel, and I don't know if his instrument was up and running at the time. I can check with him, but it's the moon is pretty faint. The problem is your light's gonna be swamped by the primary, so it's gonna be really tough to tease at the effects of changes on the secondary out of it.
Wonderful talk. Thank you. Thank you.
Thank you. Yeah, thank you for the invitation.
There are no more questions. There was the right hand, but Enrique, but it's not anymore. So don't know.
Yeah, I don't know if I have time to ask one or two questions.
Yeah, please.
Oh, awesome. Well, thank you for the talk. That was very interesting. So I have a few questions about the instrument and the standards. So what is the field of view for each of the Qs and Us?
So the whole field of view is around 4 arc minutes across. So what we do is we have all of work has, I believe, a 9 arc minute or 8 arc minute field of view. And so because the polarization is splitting the light into 4 components, what they wind up doing is masking out the central 4 arc minutes, and then that gets pushed into these 4 quadrants here. And you can see in that opening slide, there's a little bit of overlap.
Yeah.
So you can see basically this is the mask here. And, so this is 1, 2, 3, 4. The actual mask is a square that was in the center here. So the asteroid was kind of off to the center left. And so what you're getting is 4 traces that way. Because it's such a big field of view, right? Again, if this gets crowded, now you're having a whole bunch of stuff overlapping, and any asteroid off field of view here is putting stuff in. So it can get pretty confusing pretty fast.
Yes, that was my follow-up question. So have you tried any extended object at all, and how would you deal with the first order of the PGs?
Yeah, extended objects, yes, those are incredibly difficult. I actually took a few snapshots for a colleague of mine in Germany, Yuna Kwon. There was a comet she was interested in, so I took a half hour of data, sent it over to her, and it wound up she was able to tease out to basically look at in the center versus the wings, to do polarization profiles this way, this way, this way, and this way. And she's able to get some very interesting results. She just, I'm not sure if she submitted the paper or was about to submit the paper for publication. But look for that because, yeah, it's there's some interesting changes, again, with the dust as a function of wavelength that she found.
Awesome. So the other question is maybe Edgar is the expert on this, but I think there's some near-infrared polarimetry of radio loud and quasar objects. So how do you think on using those ones as a standards? I think it's on HST data that I think Edgar was the one who published all that data. I don't know if they're going to be too faint for the limit that you have, but they're like constant position angle polarization and very highly polarized.
That's really interesting. Yeah, I'll look into that. I hadn't considered using the radio log quasars, but no, that's a really good idea. I can definitely look into that. The guys who built this instrument did some calibrations, I think mostly against standard stars. And we are starting to look into some quasar polarization with this. So there's a paper that was just accepted that I gave again, another half hour data to look at blazars, the polarization of blazars across wavelengths as they change over time. So there's a lot of new applications that are coming out, but it's still early days, and a lot of people are just still trying to figure out how to apply this data. So, but I'm looking forward to seeing what people come up with this.
Awesome. Thank you so much.
Yeah, you're welcome.
So there are no more questions, Joseph. Thank you. Thank you once more.
Yeah, you're very welcome. Thank you for having me.